Hello friends, welcome to today's lecture. In today's lecture we will discuss the variational problem with the condition extremum. If we recall, we have discussed the problem, extremum problem for these kind of functional. We have x0 to say x1 and we have f of x, y, y dash and d of x, or you can say that if we have more than one curve, say y1 to yn, then it is x0 to x1 f of x, y1 to say yn and y1 dash to say yn dash and d of x, provided some boundary conditions defined at the point x0 and x1. So here these problems are known as unconditional extremum. So today we'll discuss that what happens if we put certain condition on these functions, these variable y and say y1 to yn. So that is the today's topic. So let us discuss here. So we want to discuss here is the variational problem involving a conditional extremum. So variational problems involving a conditional extremum are problems in which we find an extremum of a functional v such that the certain constant are imposed on the function on which the functional v is dependent. So here if we consider this functional which is depending on y1 to yn and define an x1 to x2 f of x, y1 to yn, y1 dash to yn dash d of x, and the condition defined on these variable y1 to yns are given as phi I x y1 to yn equal to 0 for each I equal to 1 to m, where m is some number which is strictly less than n. So to discuss this problem, let us recall the similar problem, and the similar problem is that we try to find out the extremum of the function z equal to f of x1 to xn, where x1 to xn's are variable here, and provided that certain constants are given, phi I x1 to xn equal to 0, where I is equal to 1 to m, where m is strictly less than m. So this is the simple problem posed in calculus, and to find out this problem, to find out the extremum of this problem, what we try to do here, we try to look at this constant system of constant, and we try to solve this system of constant in terms of your x1 to xm, and try to put that value of x1 to xm here in the function z equal to f of x1 to xn, and this by doing this your function z is now reduced to a new function which is having independent variable xm plus 1 to xn, and we can simply solve the condition of extremum with no constraint. So how we can do this? Let us proceed here. So the natural way is to solve the system phi I x1 to xn equal to 0, where I equal to 1 to m, the equation of which are independent. So here we are already assuming that these system of constants are independent to each other. It means that we can solve this phi I equal to 1 to m in terms of x1 to xm. So without loss of generality, I am assuming that we can solve these constant for x1 to xm. So if it is not, then we can interchange we relabel the variables, and we can always relabel as x1 to xm. So here if phi I are independent, we can solve them as x1 to as x1 as function of xm plus 1 to xn, and similarly xm to xm as a function of xm plus 1 to xn. So by doing this, this function f of x1 to xn is reduced to a new function phi, which is depending now on only n minus m variable xm plus 1, xm plus 2 up to xn. So now we can say that so the problem has reduced to investigating the function phi for an unconditional extremum in the variable xm plus 1 to xn. So we try to apply the same approach to solve the given variational problem. So how we can do that? Let us see that. So we have a constant like this, phi I x y1 to yn equal to 0, where I is equal to running from 1 to m. So we try to solve this and substitute their expression into v functional. So we are solving this for y1 to ym, and after putting this expression y1 to ym, this is functional v which is depending y1 to yn is now reduced to a new functional w, which is now depending on only on ym plus 1 to ym, and which so it is depending on now n minus m arguments that are already independent. So this is the classical approach which we apply in calculus, and we can apply for functional also. But here in this lecture we try to discuss a new approach or more convenient approach, that is the method of undetermined coefficient. So here to apply the method of undetermined coefficient, let us first discuss the case of calculus, and then we try to discuss the case for functional. So here we want to investigate the extremum of the function z equal to f of x1 to xn with the constant phi I is from 1 to m. And using method of undetermined coefficient, what we try to do here, with the help of this function and the constant, we construct a new auxiliary function z bar, which is given as f plus summation I equal to 1 to m lambda I phi I, where lambda I are some unknown parameters here, which is known as undetermined coefficients, and we try to find out lambda I in a way such that the extremum of this function satisfying this constant is satisfying the or extremum of this z bar. So where the lambda is our certain constant factor and the function z bar is now investigated for an unconditional extremum. So to find out say investigation for z bar for unconditional extremum, we simply say that let us take the partial derivative with respect to xi's and equate it to 0. So here double z bar with respect to double xj is equal to 0 where j is 1 to n. Supplemented by the constant equation phi I equal to 0, I is from 1 to m. So it is basically these are n equations, and here we have m equations. So we have total n plus m unknown, n plus m equation, which gives you say n plus m unknowns, that is x1 to xn, and these constant lambda 1 to lambda m. So this is the method known as Lagrange method of undetermined coefficient, which we generally apply in calculus. Now we try to apply the similar method for our variational problem. Okay, so here consider this variational x0 to x1 f of x y1 to yn y1 dash to yn dash d of x, and constraints are given as phi I x, which is depending on y1 to yn equal to 0 for I equal to 1 to m. Here this small problem here, it is phi I x y1 to yn equal to 0. So this bracket is here. Anyway, then the functional v bar, which we consider for from this original functional along with this constraint. So we consider this new functional v bar, which is defined as x0 to x1 f plus summation I equal to 1 to m lambda I x phi I dx, or if we denote this quantity as f bar, then we can rewrite this as v bar equal to x0 to x1 f bar d of x, where f bar is denoted as f plus summation I equal to 1 to m lambda I x phi I. Now we investigate this f bar for unconditional extremum. It means that we try to solve the system of Euler's equation for this functional f bar. It means that f bar yi minus d by dx f bar yj dash equal to 0 for each j equal to 1 to n with the constant equation, that is phi I equal to 0, I is from 1 to m. So here what we try to show here, we try to show that the extremum curves, extremum functions of this original function satisfying this constraint phi I is satisfying the Euler's equation corresponding to new functional, that is f bar. So that we wanted to prove here. So to prove this, we'll consider a theorem, but before that, we see that the how many equations we have. Here we have n equations, and here we have m equation given in terms of constant. So here we have total n plus m equations. So the number of equation m plus n is sufficient to determine the m plus n unknowns, that is y1 to yn and lambda 1 to lambda m, and the boundary condition which we already know at the point of say boundary point, say x0 and x1, which is defined as yj x0 equal to yj0 and yj x1 equal to yj1. Of course, which must not contradict the constant equation and will help to determine the 2n arbitrary constant in the general solution of the system of Euler's equation. It means that when you solve this system of Euler's equation, you will have generally second order differential equation, and when you solve this, you have 2n arbitrary constant, which we try to fix with the help of boundary conditions. So now here we try to observe that it is obvious that the curves thus found on which a minimum or maximum of the function v bar is achieved will also be the solution of the original variational problem. It means that what we are trying to do here, we are considering the functional along with variational problem along with some constant. So it means that we are considering the variational problem with conditional extremum. What we try to do here with the help of method of undetermined coefficient, we try to convert this to a problem of say finding the unconditional extremum of a new functional, say or new variational problem that we wanted to prove the equivalence of these two. Not equivalence of these two, in fact we want to show. So it is obvious that the curves thus found on which a minimum or maximum of the function v bar is achieved will also be solution of the original variational problem. How? Let us see this. In fact, the function lambda ix and yj found from the system 1. System 1 is this. Let me. System 1 is this. Basically it is system of Euler's equation along with the constant equation. If so, this will give you say lambda i's and yi. So claim is that the functions lambda I and yj found from the system 1, all the phi i's are 0, and if we take phi I are all 0, then v bar is reduced to v. Basically v bar is basically what? You look at here, v bar is defined as f plus summation I equal to 1 to m lambda I x phi I. So if phi i's are all 0, then v bar is reduced to x0 to x1 f dx, which is nothing but v. So it means that for these functions lambda I and yj, your v bar is reduced to v, and if for yj, j is from 1 to n, determined from the system 1, if we can have a unconditional extremum of the functional v bar, it means that extremum relative to all closed line curves, means all curves satisfying the boundary condition. They may not satisfy the constant equation, or they may satisfy the constant equation. Then in particular, an extremum is also achieved with respect to a subclass of curve that satisfy the constant equation. So it means that if we solve the system 1, and we can get lambda I and yj, and if yj say extremize the functional v bar, then this v bar is reduced to v with this choice, and we can say that the extremum yj, extremal curve yj, will also be extremal curve for v, because if extremum is achieved for v bar, which is on the class of all closed line curves satisfy the constant equation or may not satisfy the constant equation, then in particular it will an extremum is also achieved with respect to a subclass of curves that satisfy the constant equation. So let us try to prove the just said statements. So here we say that given the condition phi I x from y1 to yn equal to 0, where I is running from 1 to m, m is strictly less than n, the functions y1 to yn that extremizes the functional v. So this is the original functional v defined as x0 to x1 f of x, y1 to yn, y1 dash to yn dash d of x. Then these extremal function y1 to yn satisfy the Euler's equation formed for the function v bar. So v bar is defined as x naught to x f plus I equal to 1 to m lambda I x phi I d of x. We can denote this f as f bar dx for given an appropriate choice of factors lambda I x, I is from 1 to m. So and here the factors lambda I x and these extremal curves functions y1 to yn can be obtained by the Euler's equation f bar yj minus d by dx of f bar yj dash equal to 0 for j equal to 1 to n and phi I equal to 0 for I equal to 1 to m. In fact, if we can consider this f bar, which is defined as f plus I equal to 1 to n lambda I x f phi I as a function of not only y1 to yn but also a function of lambda 1 to lambda m, then this system of m equation can be incorporated with the Euler's equation. In fact, these set of equation is obtained by assuming that f bar is depending only on say y1 to yn. But if we assume that f bar is also depending on lambda 1 to lambda m, then this equation can also be considered as part of Euler's equation. Or otherwise you can simply write down that we have that lambda I and yi can be obtained by this Euler's equation and the subsidiary equation phi I from I equal to 1 to m. So and this we can do the equation phi I x from x y1 to yn equal to 0, I equal to 1 to m are assumed to be independent. So here we assume that the constants are independent constant. So it means that none of the constant can be written as linear combination of others. It means that this can be rewrite in the form of Jacobians. We can say that Jacobian of phi 1 to phi m with respect to some variable y1 to ym is not equal to 0. So here we are renumbering the variables such that we can assume like this. So without loss of generality, I am assuming that the Jacobian of phi 1 to phi m with respect to y1 to ym is non-zero. So let us come to the proof here. So in this case, the condition for extremum delta v equal to 0 takes the form x0 to x1, j is from 1 to n, f of yj delta yj plus f yj dash delta yj dash dx equal to 0, and we try to handle this part. So here we use integration by parts and denoting delta yj dash equal to delta yj dash, and delta yj at x equal to x0 is equal to 0 and delta yj x equal to x1 is equal to 0. So here we are assuming that these functionals are satisfying the boundary condition. So these are obvious from that fact. So here we can simplify this and we can write x0 to x1 j equal to 1 to n f of yj minus d by dx of f of yj dash delta yj d of x equal to 0. So here if you recall the proof of the Euler's equation, there we have the similar kind of equation, and we say that since delta yj are say arbitrary, then we can keep this summation has to be 0. But here we cannot consider right now as delta yj are completely arbitrary because they are related by the constant phi I x from 1 to n equal to 0 for I equal to 1 to m. So here we cannot apply the fundamental lemma here to obtain the Euler's equation for this. So here we can say that it follows that the variation delta yj are not arbitrary and the fundamental lemma cannot be applied in the present form. So the variation delta yj must satisfy the following condition obtained by means of varying the constant equation phi I equal to 0. So when you discuss yi equal to 0, then it is reduced to this equation j equal to 1 to n divided phi I by divided yj delta yj equal to 0. So here this delta yj is satisfying these m equation, and hence we can say that all delta yj are not arbitrary. So but here we have m equations, so we can say that only n minus m of the variation delta yj may be considered arbitrary. So what we try to do here, we multiply these equation by say lambda j and integrate from x0 to x1, we get this integral x0 to x1 lambda jx summation j equal to 1 del phi I upon del yj delta yj dx equal to 0 I equal to 1 to m. So here adding term wise all these m equation which are satisfied by the permissible variation delta yj with the equation x0 to x1 j equal to 1 to n f of yj minus d by dx f of yj dash delta yj dx equal to 0. So this we obtain by taking delta v equal to 0. Now we have these equations which we multiply by lambda j and we are getting this. We have new function, new integral, that is x0 to x1 j equal to 1 to n del f by del yj plus lambda ix del phi I by del yj minus d by dx of del f by del yj dash delta yj dx equal to 0 here. So here we introduce a new notation, that is f bar, which is written as f plus summation I equal to m lambda ix phi f I. So so if we take this new notation, that is f bar, we can rewrite this condition into this form x0 to x1 j equal to 1 to n f bar yj minus d by dx of f bar yj dash delta yj dx equal to 0. So here in this this can be rewritten in terms of f bar as follows. So here we have incorporated our constant as well as the condition that delta v equal to 0 into this integral, that x0 to x1 j is equal to 1 to n f bar yj minus d by dx f bar yj bar yj dash delta yj dx equal to 0. Now still we cannot apply the fundamental lemma because delta yj are not arbitrary. So for this we have taken the factors lambda 1 to lambda m completely arbitrary, but now let us assign some values of lambda 1 to lambda m so that this equation, so this equation f bar yj minus d by dx f bar yj dash is equal to 0 for j equal to 1 to m. So we try to find out lambda 1 to lambda m such that these m equations is true. So and what is this? If you simplify this, if you look at, this is nothing but del f by del yj plus summation I equal to 1 to m lambda ix del phi I by del yj minus d by dx del f by del yj dash equal to 0. If you look at, these are linear equation, a system of linear equation in terms of lambda I, and we can find out the solution here, solution of this system of linear equation in terms of lambda I, because the coefficient matrix, if you look at del phi I by del yj, this has a non-zero determinant because we have assumed that these phi i's are independent constant. So keeping this thing in mind, we can always find out such factors lambda 1 to lambda m such that these equations are true for j equal to 1 to m. So if we have these equations true for j equal to 1 to m, putting it into this equation, we can have that we have this x0 to x1. Now summation is reduced to j equal to m plus 1 to n. Initially it is from 1 to n, now it is reduced to m plus 1 to n f bar yj minus d by dx f bar yj dash delta yj dx equal to 0. So now this delta yj are arbitrary in some sense. So we can say that for the extremizing function y1 to yn of the functional v, this functional equation reduced to an identity for an arbitrary choice of delta yj j equal to m plus 1 to n. So now we try to apply the fundamental lemma. So how we can apply? By taking say all the variation as 0 except 1. So let us say that putting all the delta yj equal to 0 in turn except 1 and applying the fundamental lemma, we obtain this f bar yj minus d by dx of f bar yj dash equal to 0 for each j equal to m plus 1 to n. And if we so here we have n minus m equation, and if we remember, we have these m equation which we have obtained by choosing the values of these factors lambda 1 to lambda m. So this along with the these these n minus m equation, we can rewrite our set of equation as this, that taking into account the above obtained equation, we have f bar yj minus d by dx f bar yj dash equal to 0 for each j equal to 1 to m. So 1 to m is earlier one, and this m plus 1 to n, we have this equation f bar yj minus d by dx of f bar yj dash equal to 0 for each j equal to now 1 to n. So 1 to m is obtained by choosing lambda 1 to lambda m, and this m plus 1 to n obtained by applying the fundamental lemma. So we have now n such equation given here, and m set of equation given by the constant. So we have total n plus m equation. So and by these n plus m equation, we can find out the function y1 to yn, and the function lambda 1 to lambda m. So let us consider one example here, and the example is that find the sorted distance between 2 points A and B, where the coordinates of A as x0, y0, z0, and coordinates of B are x1, y1, z1 on the surface phi of x comma y comma z equal to 0. So here shortest distance, so the formula of distance is given here, I as x0 to x1 under root 1 plus y dash square plus z dash square d of x, and the condition that these 2 points lie on phi of x comma y comma z equal to 0, and we are measuring the distance only on this surface. So this is the condition we have to consider, and now this we can solve by the theorem given just now. So here consider the auxiliary function I bar equal to x0 to x1 under root 1 plus y dash square plus z dash square plus lambda x phi of x comma y comma z dx. So here we have only one subsidiary equation or one condition, so we consider only one function lambda x like this. Now here if we assume this as a new functional f bar, then we can write down the Euler's equation for this f bar, and we can say that the corresponding Euler's equations are reduced to lambda x phi y minus d by dx of y dash upon under 1 plus y dash square plus z dash square equal to 0. Similarly corresponding to z, lambda x phi z minus d by dx z dash upon under 1 plus y dash square plus z dash square equal to 0, and the condition that is phi of x comma y comma z equal to 0. So from these three equations we can find out the function y equal to y of x and z equal to z of x, on which the condition minimum of the function can be achieved, and we can also find out the function lambda x from these three equations. So here we have applied our theorem to find out the extremum of this functional this variational problem I equal to x0 to x1 under 1 plus y dash square plus z dash square d of x, provided the condition phi of x comma y comma z equal to 0. So here we stop, and in next class we will discuss when the condition is not a finite equation, but it is a differential equation in place of this finite equation. So in next class we will discuss this similar kind of problem, but the conditions are replaced by differential equation rather than this finite equation, and we'll also consider certain application of this set theory. Okay, so thank you for listening us. We'll meet in a next lecture. Thank you.